The next section of the textbook is buffers. A buffer is defined as a solution that resists change to pH when you add limited amounts of acids or bases. This is a very important concept in biology. Our bodies are buffered and most biological systems are buffered, so most of the research that biologists do are in buffer solutions. For example, when 1 milliliter of a 0.1 molar hydrochloric acid changes the pH of an unbuffered solution by 5 pH units, whereas it changes a buffered solution by as little as 0.1 pH unit. A buffer always contains either a weak acid and conjugate base or a weak base and conjugate acid. So basically it's what we just did with common ions. We did an example with a weak acid and its conjugate base in solution, and we did an example of a weak base with a conjugate acid in solution. In biology, we use something called, or biologists and most chemists even use something called a Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is derived from the Ka expression. I'm not going to go through the whole division, I don't think. But Ka is equal to the A minus times H3O plus over HA. And if I solve this for hydronium, I end up with Ka times HA divided by A minus is equal to hydronium. And then I simply take the negative log of both sides. So the negative log of Ka plus the negative log of HA over A minus is equal to the negative log of H3O plus. So negative log of Ka is pKa plus, well, let me see, minus the, well, it's still the log of HA over A minus, and the negative log of hydronium is pH. Now, you'll notice that this is a plus sign and this is a minus sign, so all I have to do is reverse this, and HA stands for the acid, A minus stands for the base, so it becomes that pKa plus the log of the base over the acid is equal to pH. So this is just a derivation of this equation here. And to demonstrate that, this is the same problem that we did for common acids, but now we're going to do it with the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is pH is equal to pKa plus the log of the base concentration over the acid concentration. So I first need to identify this, of course, having a hydrogen in front is my acid, and this is my F minus, so this is my base. I need to find the pKa, so pKa is negative log of Ka, so negative log of 6.8 times 10 to the minus 4, and that gives me 3.17. So now go back over here, I have 3.17 plus the log of the base is 0.50, the acid is 0.10. I take the log term first, so I have 3.17 plus 0.699, and when I add those together I get 3.87. And that's all you have to do. Now I'm going to flip back real quick to this one, and you will notice here when we did this, like I said, this is exactly the same problem, it's just worded a different way. Well, actually no, it's worded the exact same way, I just did a different formula, that my pH was 3.87. So I get the same pH either way that I do this. Okay. I'm also doing this one, in which, again, it wants to know what the pH of ammonia plus ammonium chloride are, and it tells me that Kb of ammonia. So therefore, this has already identified that this is my base, and so by definition, this must be my acid. Still using the Henderson-Hasselbalch equation, pH is equal to pKa plus the log of the base over the acid. Now this one, because of the fact that the base, I'm giving the Kb, it involves a little bit more work. And the work is to go from Kb to Ka, so I can find pKa. So I'm going to use the formula Kw is Kb, whoops, I'm going to say Ka first, Ka times Kb. Kw is still that 1 times 10 to the minus 14. Ka is what I don't know, times 1.8 times 10 to the minus 5th. So 1 times 10 to the minus 14th divided by 1.8 times 10 to the minus 5th is equal to Ka. So Ka ends up being 5.56 times 10 to the minus 10th. And then I find the pKa by taking the negative log of 5.56 times 10 to the minus 10th. And I get 9.26. Now I'm ready to plug it in here, so I have 9.26 plus the log of 0.40 divided by 0.30. Again, do the log term first, 9.26 plus 0.125, and I didn't round anything, so in my calculator I got 9.38. And just to go back and check, this is the same problem. In fact, I just copied and pasted. This is the same problem we did back here, and you will notice that this pH and the 9.38 is exactly the same answer. So you can do them either way. You will probably see from future classes, I know biochemistry for one that most of you have to take, focuses on the Henderson-Hasselbalch equation instead. And that is the end of this video.